In this lecture, we're going to continue with the topic on wave transformations. As a train of wave propagates towards the shore, these waves enters into the region where the water depth reduces, B becomes less, and as a result of that, we already discussed previously that the wave celerity decreases and wavelength also decreases. Is analogous to if you run towards an area which is shallower and you feel more friction on the surface, then your speed reduces, and at the same time the energy gets squished together so that the wavelength becomes shorter, and not only that, the wave height also becomes larger. This due to the effect of the energy being concentrated into the smaller water column, and it's also due to the fact that the trailing waves actually catches up with the leading wave, which is related to the change of the wave group celerity compared to the individual wave celerity. Consequently, the water particle motion also becomes faster and faster, U increases, and so eventually the orbital speed actually exceeded the wave speed, the wave celerity, and causing the wave profile to become increasingly asymmetry, and so become increasingly unstable. Finally, the wave will break to dissipate this concentrated energy in its crest. We have discussed previously about this figure, and our previous slide basically also explains about this figure, and you can try to use this figure to explain again what actually happens when wave propagates from deep water region to the transitional water to the shallow water region. On this slide, we see the typical circular orbital motion of water particles in a deep water wave, and also a trochoidal profile in the shallow water wave. Specifically, we want to look at the trochoidal shape here, which is characterized by long flat trough along the lower part here of the wave, and a short sharp crest. And we also notice that the crest amplitude is higher than the trough amplitude. Also, the crest velocity is actually faster than the trough velocity. Overall, you notice that typically when a wave has undergone the transformation to in the shallow region, typically the wave height is much larger compared to the wavelength, such that the wave steepness would have increased. It is asymmetry and relatively unstable compared to the sinusoidal profile of a deep water wave. This slide here shows a typical asymmetry wave. If we ignore the bottom slope, wave breaking typically will occur when the wave steepness exceeds a critical value defined by this expression. So basically, the wave will have wave height and wavelength that keeps on changing from one point to another point if it fills the water depth, the bottom. So if the wave steepness, the HOL, reaches the maximum or the critical value given by this expression, then we expect the wave to begins to break. So the critical wave steepness is given by 1/7 tangent hyperbolic of 2 pi d over L. as before, since we have a hyperbolic term in the equation, we can actually make some simplification in deep water and in shallow water. In deep water, the tangent hyperbolic term will equals to 1, so that the critical wave steepness equals to 1/7, meaning to say that if the wave steepness in deep water reaches 1/7, it will break. Of course, we might also see a breaking wave in deep water, especially in a storm event, whereby the wind keep adding energy to the wave so that the wave height keep increasing, and eventually when HOL exceeded 1/7, waves breaking will occur even in deep water, even in offshore. In shallow water region, the tangent hyperbolic term, tangent hyperbolic 2 pi DOL is almost equivalent to 2 pi DOL. So the critical wave steepness, HL maximum, is given by this expression. Let's look at this example. Show that an incoming wave with a wave period of 10 seconds oriented at 35 degrees with the shoreline will not break at location A, which is given by a water depth of 100 meter and a wave height of 2 meter, but will break at the location B, which has a water depth of 2.3 meter. So this problem is again a continuation from our earlier discussion. For a wave with a wave period of 10 seconds, we can solve easily to show that the wavelength and the wave celerity are as shown here. And so in this case, the DOL is 0.6, is actually a deep water wave. Since we are talking about a water depth of 100 meter and a wavelength of 156 meter, and the DOL equals to 0.6, is a deep water condition. So in order to check whether the wave will break at this deep water location or not, we check the HOL maximum, or the critical HOL, which of course is already known to be 1/7, that is 0.143. But here, since the wave height is 2 meter and the wavelength is 156 meter, we know that the actual wave stiffness here is 0.013. 0.013 is actually smaller than 0.143. That means it did not reach the critical value. Alright, so HOL is less than the HOL maximum. So in this case, the wave will not break at this location D equals to 100 meter. But if we move on to the location B, whereby the water depth is 2.3 meter, we solve the wavelength and the wave celerity. Actually, do you need the wave celerity here? I don't think so. Yeah, you don't need the wave celerity. Okay, so it's not even necessary to be here. What you need is the L, so that you can calculate the DOL. You actually need the DOL eventually here, multiplied to 2 pi. Okay, so anyway, if we have L already, we know DOL gives a value of 0.048 here, meaning to say that this is a shallow water location. So for shallow water location, the HOL max, or the critical wave steepness, is given by this expression. So we calculate that, we get 0.043. So this is the critical value, but what about the actual value that is happening now in this location B? The H is actually 2.33 meter, whereas the L is 47.5 meter. Where do we get the 2.33 meter from? Okay, it's actually from example 4.18-1. If you can't remember the example, let's try to recall here. Why would the wave height change from 2 meter to 2.33 meter? Well, in this case, it may be due to refraction, because the question says that the incoming wave is oriented at an angle with the shoreline. Okay, so that is the reason. Another reason is Shoaling effect. So if you go back to example 4.18-1, you should be able to see how we use the Shoaling coefficient and the refraction coefficient to calculate the wave height at this location B, which is 2.3 meter. So now since this location has a wave height of 2.33 meter and a wavelength of 47.5, so we found that the HOL, which is the wave steepness, is 0.049. If we compare this value with the critical wave steepness, we found that the HOL is larger than the HOL max, which means that yes, the wave will break in this location.